So we have discussed about Biot-Savart law, and we have understood what will be the value of a magnetic field, the strength of the magnetic field dB for a small current element dl. Okay, and the formula we know. So using that Biot-Savart law, as we have discussed before, that using that Biot-Savart law, we are now going to derive an expression for magnetic field. Okay, magnetic field due to a long straight current carrying conductor. Long straight current carrying conductor means you have a conductor which is straight, it is long. So long, you can say it is infinite on the both end, or maybe infinite on one end. Okay, or not infinite on any end, basically finite length, anything but a long straight conductor. And we are going to find the magnetic field at a certain point P. Okay, so this is what we need to find the expression for. Now this derivation is obviously not, derivations are not important for any competitive exam, but this is a CBSE board exam and PU board exam, both CBSE PU board exam ka standard derivation. Okay, 5 marks derivation question this is. So you need to understand the derivation very carefully. It becomes a bit confusing, thoda sa confusing hai. Okay, need to understand the derivation and draw this diagram right away. Don't look at, watch this video, this is not an entertainment video. Okay, so please don't just watch it, draw the, pause the video, draw this diagram, do the derivation as I'm doing, then only you will get it, or else you will won't. Now this is our wire. Okay, this is our conductor. You can see this is the conductor, and for now I am going to assume that this conductor has a finite length. Okay, it is a finite length conductor. Later on we can we can make it infinite and so on. So why now finite length? And this is the point P where you are supposed to find the magnetic field due to this length of the conductor. See, Biot-Savart law have only told us about finding the magnetic field for a small current element dl, only the small current element. But now we don't have a small current element, we have the whole conductor in front of us. So we need to find the magnetic field for this whole conductor at this point P. Now for this, what I'm going to do is to again assume one small dl element. Okay, this current element dl, current element, again current element dl, this will be the direction of this current element dl, and this will be the value of the position vector of the point P with respect to this dl. Okay, with respect to this dl, this is the position vector, that is this r vector, and this becomes my theta angle. Again, what was theta? Theta is the angle between the dl vector and the position vector r vector. So this is my angle theta. Now the perpendicular distance, you see this r is not the perpendicular distance from the wire. It is not the perpendicular distance from the wire, it is the distance from the dl point to the point P. So first we need to find the perpendicular distance. So this becomes our perpendicular distance from the wire, which is a. Okay, so perpendicular distance from the wire, which is a. And then from the point P, you are going to draw the a line to the two ends of the conductor. So from the point P, you first draw the line xp. Okay, and this will become your this will become your certain angle. You will say this angle to be phi 1. Okay, you will say this angle to be phi 1 and this angle to be phi 2. Okay, this angle will become phi 2. Now be very clear about the angles. You see, you have three angles here. You have a theta here, you have a phi 1 and phi 2. This becomes confusing later on. So you only use the phi and theta notation. Do not change this. Don't ever write this two angles as theta or this two angles as alpha, beta, or any other thing, because in every study material, every books, these angles are written as phi. So if you use a wrong notation later on, you will get confused. Okay, so the phi 1 and phi 2 are the angle, this from angle from this point to this line, this angle is making with the perpendicular line. So this angle becomes my phi, and this is my phi 2, phi 1 and phi 2. Now, next is this from the perpendicular. If P, if I draw the perpendicular, then this point Q, and from this point to this point here, the DL, this is the length L. Okay, this is the length L. So draw this diagram, write all the values, make this conductor I current, DL element, theta, phi, P, A, this length here, r vector, write all the values, then proceed ahead with this derivation. Okay, so we will start with the Biot-Savart law. This is our Biot-Savart law. This is dB is equal to mu naught by 4 pi ideal sine theta by r square. Now look at this diagram again. From the right angle OQP, OQP, this angle. Okay, this is right angle, as we can see, right angle OQP. Now in this angle we see this angle is theta, and this angle is phi 1. So let's take this as phi right now. Okay, take this as phi right now. So here theta plus phi will be is equal to 90 degrees. So that means theta will become 90 minus phi, and as theta is 90 minus phi, that means sine theta will become cos of phi. So we can replace the value of sine theta from this here and write as cos of phi. Okay, so in our Biot-Savart law we have to change certain values. So we have to change the value of sine theta, we have to change the value of r, and we have to change the value of dl. Okay, do remember three values you have to change. Sine theta value you have to change, r value you have to change, and dl value you have to change. So sine theta will become cos phi. I hope you understood that. Now next will be value of r. So what is r here? So you see in this particular right angle triangle, you can write that cos of phi. Okay, cos of phi is equal to a by r. Okay, look very closely. Cos of this angle is equal to the base by the hypotenuse. Okay, and cos phi will become a by r. So obviously r will become a by cos phi, and that is a sec phi. Okay, so r will become a sec phi. So obviously r square will become a square sec square phi. Okay, so I have changed the value of sine theta as a cos phi, then I change the value of r square as a square sec square phi, and then I will change the value of dl. Now how to find this dl? Now again in this triangle only you will find that this value is l. Okay, this value is l and this is a. That means if I find the tan of this phi angle, okay, or this angle, if I find the tan phi, it will become what? It will become L over A, perpendicular over base, or opposite over adjacent. So tan phi will become L over A, and L will become A tan phi. DL differentiating, because we don't need L, we need the value DL. That means we have to differentiate it, and on differentiating this, we will get DL is equal to A tan, differentiate when you do, say, a sec square phi d phi. Okay, a sec square phi d phi. So now that we see, we have successfully converted all the three required values. That is, sine theta is now converted into a cos phi, r square is converted into a square sec square phi, and dl is also converted into a sec square phi d phi. Okay, a sec square phi d phi, and you see all these three values are again put up in the replaces the original value. So dl will become my a sec square phi d phi, sine theta will become my cos phi, and r square will become a square sec square phi. Now in this expression, very well, you can see that you can take out this sec square phi will go off, and this one a value will go off, and the square term will also go off. And what are you left with? You are only left with this cos phi d phi. Okay, only this cos phi d phi, and the denominator mein this is a. So your expression will then look like mu naught I. Okay, mu naught I by 4 pi a. You see, mu naught I by 4 pi a, and then cos phi d phi. Okay, mu naught I by 4 pi a cos phi d phi. Now, after this, you will obviously have to integrate this value to find the value of the actual magnetic field, because what you have found out the value of dB, that is the small magnetic field due to the current element dl. But again, that's not simply the current element. We have to find the magnetic field due to the entire conductor. So here we have to do this. Now, when we integrate this, what should be the integration? The limits here. So limit will become minus of phi 1 to plus of phi 2. Now why minus of phi 1? Again, as you can see, this is phi 1 is at a negative. So this is a negative angle. We have to take negative phi 1 to positive phi 2. Now this will become phi1 to phi2, and then you will integrate this. Cos phi will become sin phi, and cos phi d phi will become sin phi. You put the limits as minus phi1 plus phi2, and it will become sin phi2 minus of sin phi, minus of sin of minus phi. Okay, so minus and minus, it will become plus. This trigonometry thing you already know, and this will be your final value as mu naught I by 4 pi a sin phi 1 plus sin phi 2. Okay, so again go through the whole this derivation. This derivation is not important if you are revising this topic for, if you are going through this video and revising this topic for board exam or PU exam, then you must go through it. If you're simply going through the topic for quick revision, don't. So see, this derivation is not relevant for any competitive exam. Now at the end of this derivation, what do you get? You get this whole thing as mu naught I by 4 pi a and sin phi 1 plus sin phi 2. And the flow of the derivation is very simple. You will start from the Biot-Savart law. You keep in mind that you have to change these three values, sin theta, dl, and r square. When you change these three values, you are eventually going to get this. Okay, you are going to get this, and then you integrate this from minus phi 1 to phi 2, and your final value. Now, if this is the value that I got in phi 1 and phi 2, now think about the phi 1 and phi 2. Phi 1 and phi 2 was originally the two angles made by the two ends. Okay, from the point P to the two end, isn't it? That was your phi 1, phi 2. Look here, what was the phi 1, phi 2? You see, phi 2 is this angle, this value. Phi 1 is this one. Now, if for some reason, if I say this conductor is infinite, that means from this end it is infinite and this end it is also infinite. In that case, if it becomes infinite, that means phi 2 will become, phi 1 will become 90. Both of them will become 90 degrees. Okay, both of will become 90 degree. If this end becomes infinitely long, then this phi 2 angle will keep on increasing. It will eventually become 90 degree at this, and this value becoming infinity. Now, if phi 1 and phi 2 both become 90 degrees, that means it is infinite on the both the ends. Okay, infinite at both ends. Then this will sin 90 here, sin 90 here. This will become what? 1 and 1, that will become 2, and 2 will cancel here. That means B will become what? Mu naught I by 2 pi A, where A is the perpendicular distance from the wire. If you're doing the same thing for one end of the wire, okay, if you're doing the same thing for one end of the wire, that means your one end is infinite and the other end is not infinite. The other end, you are finding the magnetic field at this point P. Okay, then your formula again, mu naught I by 4 pi A sin phi 2 sin phi 1. Okay, so in this case, what will happen that as this end is infinite, so sin phi 2 value, the phi 2 value will eventually becomes 90 degree. Okay, the phi 2 value will eventually become 90 degree, and this value here will become what? 1. And then the phi 1 value, this value here is 0 degrees because there is no angle here. Okay, you are finding the magnetic field at one end, so phi 1 value will become 0, and as it becomes 0, it's sin 0. So this will be your magnetic field mu naught I by 4 pi A. Okay, so this particular concept is important. There are many questions in your exercises. Go through the exercise. We will discuss this in class as well. Go through the exercise, and there are variety of different condition for this. For example, you will get questions where you have to find the magnetic field at the center of the square. So at the center of the square, again, you're going to consider this as the current wire. Okay, this current wire. Okay, current is flowing like this, and you have to find the magnetic field at this point. So this particular formula will be used in many places for finding magnetic fields.